me the it's giving me the red light.
The red light is the good light. Okay, it looks like we're doing something. Excellent. All right, so we are live, ladies and gentlemen, so we are looking forward to this. Welcome, everyone. I'm Dr. J.D. Armstrong. I am the director of the High Star program. And for those of you who are unfamiliar with the program, it's basically a week-long summer camp doing astronomy. We do astronomy and physics and anything space-related. And the students have been working on some independent research with mentors. And at the end of the week-long course, we encourage them all to present, and all of them volunteered, and only 2 of them had to have their arms twisted until they were in tears before they volunteered. So our first group, we have 6 groups, I believe. And our first group is the Asteroid group. They are comparing methods of spectral classification of the asteroid Iris. And the presenters are Edward Diven. Edward is a returning High Star student, second time around. Eskin Guerin also is a returning High Star student, and Zach Teagarden, also a returning High Star student. So these are a little more veterans here, and their mentor has been me, the fabulous Dr. J.D. Armstrong. Okay, so I will now go ahead and share their slides and let them present. So we should be sharing your slides right now, guys.
Okay. So hello, my name is Eskin.
I'm Zach.
And I'm Edward.
And for our project, we worked on comparing methods of measuring asteroid spectral types.
So we studied the asteroid Iris. It's a large asteroid that's currently in orbit of the sun. And we analyzed it using graphs called spectra. And they're essentially just charts of an object's brightness on the y-axis versus specific wavelengths of light on the x-axis. So yeah, that's the main way we studied Iris. Next slide. Yeah, that was
Yeah, that was his.
Yeah, I just presented that slide. Do you want me to do that again?
It's not showing up yet.
I mean, okay, should I just say it again?
You are on slide 2, background.
Yeah, I'll do it again. I just presented it, but yeah, I don't think it was sharing your screen. So we studied a large asteroid that's named Iris, and it's currently in orbit of the sun. We mainly analyzed it using spectra, and these are essentially charts of an object's brightness on the y-axis relative to specific wavelengths of light on the x-axis. So that's the main way we analyzed Iris. Next slide.
Okay. So a solar analog is essentially a star with the same color as the sun, and we use it to take out any sunlight interfering with data. Next slide.
So our objective for this project, or main focus, was to create a spectrum of Iris using our own photometry and compare it to a spectrum of Iris made with a spectrograph. And we just wanted to see if our photometry kind of compared well to the photometry done with the spectrograph and see if both of them were accurate. Next slide.
So for the first, we first had to match the spectrum from the asteroid to the spectrum of the solar analog. Next, we divided the brightness of Iris by the brightness of the solar analog, and we made a spectrum from that. Then using images of Iris, we used SAO image DS9 to measure the amount of light coming from Iris. And we also measured solar analog to see how much light was coming from that too. And we use that to take out any sunlight coming from our data. Next slide.
So once we get the data from DS9, we did the same procedure for canceling out the sun's light as we did with the data from the spectrograph. And next, each of us made a photometric spectrum of Iris through different wavelength filters. The filters that we used were G, R, I, Z, and Y. Those are green, red, infrared, further infrared, and even further infrared. And once we did that, we compared them to the spectrum made with the spectrograph. And with both of these graphs, we could then see any differences or resemblances between the two spectrums and see how they matched up and all that. Next slide.
So our initial spectrograph is on the top right of the screen. You can see essentially it has a serious spectral line under 8,000 angstroms on the x-axis. You can see there's a huge line, and that's essentially a spectral line. And we assumed that was likely interference from the sun. So after correcting with the solar analog and dividing all of our data points from Iris by all the data points from the solar analog, we got the graph on the bottom left, and that's what we call the relative spectral albedo. That essentially means it's the amount of light, or it's the light we saw reflected from the Iris. And so you can see our correction essentially eliminated all of the interference from the sun. And by doing that, it sort of supported our method that dividing by the solar analog removes all interference from the sun. Next slide.
So for our final results, as you can see on the right, the blue data points are the relative spectral albedo made by the spectrograph. And the other data points is our spectra that we made each. And our data points matched up pretty well with the one made from a spectrograph. And this graph basically shows us which wavelengths of light are being reflected by the asteroid. Next slide.
So some of the problems we encountered were that the wavelengths weren't always matched. So in our spreadsheet, we had to go through and we had to rematch 3,000 data points, which was sort of time consuming. And we also had to redo some photometry because our aperture radii weren't always global. So we had to redo that because keeping the aperture radius constant was pretty important to getting accurate results. And then we also had a few technical errors, and those always need to be fixed. So those were the main problems we encountered.
Next slide.
Sorry, yeah, next slide.
So to continue this project, we want to still continue to do more photometry on asteroids, but we want to focus more on asteroids with unknown spectrums. And since doing this project, we already proved that our method of finding the spectrum of asteroids works and it's pretty accurate. So we want to actually go a step further now and find the composition of asteroids based off of using the Tholen spectral types. And the Tholen spectral types are basically just different classes of asteroids. And using these, we can determine if an asteroid is more stony or more metallic, and just determine the composition of it with more accuracy. So that's what we want to continue to move forward with doing. And yeah, next slide, please.
Thank you for listening. Questions?
Yeah, thank you.
Yeah, does anyone have any questions?
I think you're muted, JD.
Yeah, I can't hear you, JD. Yeah, you're not muted anymore. Oh, wait, no, are you? No, you are muted. Never mind, sorry.
You're muted.
Yeah, you're
Yes,
muted.
I am muted.
Now you're.
That's why I was advised not to mute myself. Okay,
Yeah.
so if there are any questions, you can, if you're following on YouTube, you can send them through the YouTube channel, and hopefully I will get them in a timely manner. Let me see here. Oh, how did you choose your solar analog? I think, go ahead.
Basically, a solar analog is just a star with a sunlight color. So it doesn't really matter what star your solar analog is, just so long as it's more of the same color as the sun. Because the solar analog just basically gets the sun's light out of the way, because we can't look directly at the sun because of it's too close and it's too bright. So we use just a different star further away to reference what the sun is like.
Yeah, the sun telescope. So.
I hope that kind of gave a good definition of that.
Okay. So in other words, let me summarize it. You had a list of solar analogs, which are stars that are supposed to look like the sun, and you kind of chose those out of convenience because it's easier to look at these stars than it is to look at the sun. Is that a correct summary?
Yes.
All right, great. So we have another question here from Kurt Dodds. On your last plot, your data points are clustered in little vertical groups. Why is that different than the blue points?
Are they plotted in little vertical? Okay, I see. So those aren't actually supposed to be little vertical groups. Those are 3 different sets of data. Jade, you can share that if you want. It might make it easier to explain. But so me, Eskin, and Edward each did our own follow-up on, so this graph right here, we each did our own photometry in DS9. And so those 3 different colors, you can see yellow is my photometry, red is Eskin's, and green is Edward's. So it's not supposed to be vertical. It's supposed to be like following a trend of the blue line or the blue kind of cluster of dots. So the green line makes a curve, the red line makes a curve, and the green dots make a curve, the yellow dots make a curve, and so do the red dots. So it's basically just supposed to be sort of mimicking the blue cluster of dots to show that our method was accurate, our method of correction.
And going off of that, the reason that they're not all the same is because we all use different aperture sizes, which accounted for different amounts of lights inside of the aperture. So that made it a little bit off, but as you can see, they're all kind of in the same area.
Yeah.
It's following the same pattern.
Any more questions?
Any other questions? All right. Well, let's thank our speakers. So everyone do a virtual clap if you would. And I will switch over to the next group, which is dipping dust, if I recall correctly. Yes, dipping dust. And so our next speakers are going to be talking about dipper stars, and this is a phenomenon that is caused by comet-like dust. Our speakers are Holden Suzuki, who is a returning student to the High Star program, also one of the youngest ones. Jed Orion Teagarden. Sorry, I don't know who Jed is. I only know Orion. With a name like that, you have to use the name Orion. And Orion and Zach, in case you're wondering, they are brothers. So this is the a little bit younger model. And we have Michael Wong, and they have been mentored by Dr. Eric Gaidos and Rochelle Kavatic. And are you guys ready to go?
Yep.
Okay, I will start actually sharing it this time, not just displaying it on my screen. And here we go. I think we should be sharing that at this point.
Yeah. So this is Dipping Dust by me, Michael, and Holden. So next slide. So MY Loop is the star that we're researching. And MY Loop is a variable star that we observed in 4 different color bands: red, green, infrared, and ZS. MY Loop is a very interesting star because there happens to be a lot of dust near MY Loop, as it's in the Lupus star-forming region. When the dust passes over MY Loop, it can cause the light to scatter or make MY Loop less bright. Dust grains scatter and absorb light, causing objects to appear redder and dimmer than they actually are. This is referred to as interstellar reddening. So yeah, next slide. So, what is a dipper star? A dipper star is a star that has a quasi-periodic dipping sequence usually caused by dust. MY Loop is one of many dipper stars. So why should we care about dipper stars? So people care about dipper stars because the implications of different bands in higher colors can tell you about the types of dust that may surround the star. So why is dust cool or interesting? Comets have potential to transit a star, and the dust from comets causes light to scatter in different ways, depending on the size of the dust grains. And so that's pretty interesting. So next slide. So our question and hypothesis. So our question is what inspired this experiment, and it's how large are the dust grains transiting the star MY loop. Our hypothesis is that we will be able to determine the size of the dust grains using photometric data and the principles of Mie and Rayleigh scattering. And Mie and Rayleigh scattering can be represented by the image on the right. We also think that the different color filters we will be using will affect the light curves and the data. So next slide.
Different bands are important as they allow us to see what kinds of dust we're seeing, as dust refracts things differently depending on the size of them. So that was mentioned previously. And as stated before, we used red, green, infrared, and beyond infrared. ZS just means beyond infrared. So these images were all taken at different times in these 4 bands. Moving on. We had to correct for the influence of clouds and the photometric data of stars. In this image, we used reference stars to calculate and eliminate the cloud factor. As you can see, the purple arrow is pointing towards one of our reference stars, and this red arrow with the that's pointing towards the green circle is my MY loop. And so we corrected the data to the true magnitudes of the stars instead of what we were seeing, which was influenced by clouds. Next slide.
So here are our results. As you can see, we have these graphs are 4 light curves for each of the 4 bands we use, green or G, R, I, and Z. Next slide. So here are the extinction versus reddening curves that we made using those 4 light curves mentioned earlier after we calculated the magnitudes, after correcting for the data. So extinction is the x-axis and reddening is the y-axis. As Orion mentioned earlier, extinction refers to stars appearing dimmer than they actually are, and reddening refers to stars appearing redder than they actually are due to scattering. This would be circumstellar reddening, so it's because it's dust around a star. So as you can see, the slopes or like the increases of all of the graphs are positive, which indicates a positive correlation between extinction and reddening. Next slide. So because we see a positive correlation because we saw a positive correlation between extinction and reddening, we can infer the size of the dust grains are small, because small particles cause circumstellar reddening and larger ones tend not to. So if you look in the graph in the top right, we'll see a picture. This is an interstellar reddening versus, an extinction versus reddening graph for the star RY loop, which is in the same region as MY loop. As you can see, small dust has a positive slope, like the data for RY loop, which is that black line. And big dust tends to be fairly level. So as a result, we can conclude that the size of our dust grains was small. Now, of course, size is relative. And so if the typical size of a dust particle is about a micron or 10 to the negative 6 meters, we can infer that the dust grains, that were transiting MY loop were smaller than that. We also learned, so in the process of this experiment, we learned a lot about Dipper stars, how different color bands affect data, how dust scatters the light, and we also learned how to correct data to account for influences like the clouds, as Holden mentioned. In terms of what can be done in the future, one thing we could do is actually determine the size of the dust grains, as opposed to just kind of figuring out, well, is it small, is it big? We could also reanalyze our procedure for errors and touch up on our reddening graphs and photometry. Next slide. We'd like to extend our gratitude to Dr. J.D. Armstrong, Dr. Eric Gaidos, and Rochelle Kabadik for their wisdom and guidance. Without them, the project will not have been completed. We'd also like to thank the Los Cumbres Observatory for providing us with the images necessary to conduct our experiment. And we'd also like to thank the Institute for Astronomy and their associates for providing us with this opportunity. We had a lot of fun. Next slide. And last but not least, these are the references for our research. Yeah. So that's it. Thank you.
Okay, I will stop sharing here. And if there are any questions, hopefully we can get these in a timely manner as we did on the last one. Wood Guy 808 says that hand stars rule. Fan stars rules. So, okay, yes, we all love fan stars.
Might be a bit biased in that regard.
And Rochelle Kabatek says, great job, guys. So you have impressed at least one of your mentors. Okay, so here's a good question. How long were your time series of observations, and did you detect any variability as a function of time?
So I believe we collected observations over a span of about 50 days. I'm not sure what the, so our actual data was in terms of
Modified Julian date.
Yeah, modified Julian dates. I'm not really sure what the conversion is insofar as that is. I wouldn't say we really noticed any variability with respect to time. I mean, well, there was like the photometric data changed, but because we didn't compare the data with respect to time necessarily, I'm not sure if we could draw any conclusions definitively. Holden, Orion, do you have anything to say about that?
Oh.
Yeah, all stars kind of fluctuate from over time, but I don't think the time was super correlated to the brightness.
Yeah, so of course there were fluctuations, but in terms of we can't say necessarily whether or not there was like the variation was
Correlated.
significant, because we didn't perform any like statistical analysis in that regard. Yeah, hopefully we answered your question.
Okay. Got another question of, do you have a sense of how big or where the dust is for the star?
So the dust would have to be under the size of the wavelength. So it's very tiny. It's like under a micron, and that's like
under half a micron even.
Oh, she asking like where it is, like where it came from?
Yeah, if you had any idea where it came from, I believe is what Jamie Taylor.
I believe it came. We suspect it came from a comet, which is sort of like a rocky ball of ice. They're interstellar objects that can transit a star, which means they can block light in front of a star. So if I have like my star and there's a comet, right? It's gonna affect the photometry or the data that we get from how bright the star is. So by analyzing the change in light, we can figure out, like how big the dust grains are. Because if I'm looking at the star with looking at just the star straight on, versus if there's like something blocking the star, it's going to look different. And so we can observe that change, and by observing the light from the star in different color bands, we can determine whether or not the star's light became redder. Right? So it's not just the comet, like the solid object. The comet also leaves dust, right? Because comets are not like they leave dust, right? And so that dust by the comet sort of causes light to scatter, as Orion mentioned so eloquently earlier. So by measuring the changes in photometry or of the light of the star, we can determine whether that transiting occurred. Hopefully I answered your question.
Okay, it looks like we've got time for one more question, and I also see a comment that I'm going to share with you in just a moment. So the question is that it looks like the dust is larger than typical interstellar dust. Do you have any idea if is that expected or is that surprising?
It's
I would say it's, sorry, you answered? Sorry, you can go ahead.
I guess we weren't really sure how large we were expecting the dust to be. We were just expecting that there was going to be dust. So we didn't really come into any expectations about the size.
All right. So in other words, the main point was, hey, let's measure the size of these dust grains, and oh, that's what they are. Is that about right?
Yes, and certainly for a future experiment, we could investigate why those dust grains were larger than average. It's certainly something we could look into. So thank you.
Okay. All right. And then we have one comment from Ali that says, awesome job. And I'm sure that at least one of you knows who that Ali is. All right, well, let's give everyone a virtual clap here for a virtual round of applause for these guys. I think they did a wonderful job. And we will move on to our next group, which is another transiting type of project. It's revisiting exoplanets with TESS. So our presenters are Wilson Cho, Pono Fortune, and Gabe McClipp. And Wilson, I hope I pronounced I pronounced your name correctly. Wilson Chow.
Yes.
I believe. Okay, great. And Wilson's another one of our young returning high star students. Previous research has been on the SpaceX Tesla, I believe. Is that right?
Yes.
All right. Pono Fortune is a new member of our group and has done some, but has a interest for exoplanets, and we're really glad to have him. Gabe McClipp is the third member of this group. He's done a little bit of work on a repeating supernova. He is a returning high star student as well. The mentors are Nick Saunders and Jordan Vaughn, and I should mention that Jordan and Rochelle Kabatic, they're both alumni of the program that have gone on to college and have come back to us to help the next generation of students. So Nick Saunders is a graduate student over at IFA Manoa, and so Nick and Jordan are the mentors. And I will turn the time over to you as soon as I get this presentation thing going. And I should share that. And hopefully this is the right one. I'm going to take just one moment and mention to the other groups, the STAR groups, that if you want me to share your presentation for you, please get me that email ASAP. All right, turning the time over to Wilson, Pono, and Gabe.
Hey, so our project is basically about we're revisiting exoplanets with the new TESS telescope to see if their data from their last observations still holds up, and if we calculate our own data, if it's somewhat similar to what other people have gotten. All right, next one. Okay. So before we start off, we're gonna have to explain some big words in case some of you don't understand what they are. So there's four of them. The first one is exoplanet, which is basically a planet outside of our solar system, like orbiting another star. There is light curve with a C, which is a graph of the light brightness, the luminosity from a source over a period of time. And light curve with a K is a coding software written in the language of Python, and it makes it easier for anyone to download data from space telescopes and do basic astronomy. And then TESS, transiting exoplanet survey satellite, it was the telescope to discover the exoplanets, or yeah, that we got our data from. All right, next slide. So currently there are 4 main ways to discover exoplanets. There is direct imaging, which speaks for itself. You just point a camera or a telescope and you take a picture, which is very, very hard to do. And then you got a more common, or not more common, you got micro lensing, which is the same rate as direct imaging. You can see the graph down here, what is been discovered by what. Micro lensing basically is you have a light from a background source. It's bent by the gravitational pull of something like a planet, and then the images of that light source become distorted, bent, or maybe even given multiple pictures of the source. And then the most common way is that you have transit, or the transit method, which is basically you're observing the brightness, the luminosity of a star, and when the planet orbits it, the brightness will drop. It just drop ever so slightly. And then the last kind is radial velocity, is when there's a star and planet, and as the planet orbits the star, it tugs on the star a little bit, and when the star moves to and away from us, it'll slightly shift in color. All right, next slide.
So purpose. So we know
Did you get that? I said next slide.
Yeah. So purpose. So we know that TESS is a space telescope. So
Okay.
basically, there's a telescope that was launched into space, and it was really new, and it was called TESS. And so its main objective was to basically have high precision observations from space in the exoplanet systems. So what we did was we uploaded TESS data and measured the period and depth of transits for known exoplanets. And then we basically used this to find the planet's year and size of the planet. And we also compared our results to other published scientists. Next slide, please. And so moving on to missions and goals. So we analyzed and obtained our data from TESS, and as a method to revisit different existing planets with improved data from the NASA Exoplanet Archive. And so using the transit method, we measured the dip in the star's brightness. So when the planet passes in between the star and the telescope, you would see a dip in the curve. And so graphing the light curve as an explanatory way to notice our fluctuation in brightness. And so we obtained the measure of orbital period, the days, depth of transit, and transit time. And then we basically, a few further things that we were planning to do was to explore the overall temperature of exoplanets and determine if they're habitable. Next slide.
So the methods we will be using, or the methods that we used, were learning how to use Google Collaboratory and got used to the Python coding language. Another method we used was finding planets on the NASA Exoplanet Science Institute NEEXSCI website. We learned how to download the test data and create a light curve to show how the planets transited. We learned how to flatten/fold the plot to zoom in on the transit for descriptive analyzing. And we also learned how to graph the period of transit in days. JD, next slide. Some equations and formulas we used. We used the box least squares algorithm. Find the best box to each transit, and then it would tell us the depth and period of it. Next slide. And another equations we used was calculating the planet's radius. So the equation on the top is our final one. Now, what it means, r with small p is the planet radius, which is what we want to find. The r with the star is what we looked up, and it's the radius of the star. And the depth is the transit depth of the transit, which is what we measured. Next slide.
Okay, that's all said and done. It's time to look at some exoplanets. So this one is called TRES-4 b. So basically, this first little graph in the left is the star's luminosity we observed, and every little spike is a transit. So what I did is I zoomed in on one of those spikes, and below it, that's what it looks like. And then I took the BLS periodigram, and it stop laughing. It, like you said, it fits the best box for each transit, and it tells us this depth and what is it? Period. Sorry, depth and period. So this is the entire observation, and then you zoom in over here to get a more detailed description. Then what we did is I calculated its orbital period by these BLS boxes, and then you take the orbital period and then I made my own scatter plot of the transit. It's the scatter plot of transit, and the calculated data I got is very similar to what the archive observation actually was. And if you look here on the actual transit, it's only like a 1% drop. So even though it's a very little sudden decrease in brightness. Okay, next slide. So this is another exoplanet I did called WASP 77AB, and it's pretty much the same. You take the original observation, you zoom in on a transit, use the BLS formula to get its best match to find its period and depth, and then you take those calculated period and depth and make your own. I made my own scatter plot. This one's a lot nicer than the previous one, and this transit has a depth of 1.5, so the star's brightness went down by 1.5. And since we got the orbital period of the planet, we could take that, with the orbital the radius of the star from the archive, we could calculate the radius of the planet, which I thought was pretty cool. All right, next slide. So when it comes to looking for transits and exoplanets, sometimes they work, sometimes you get a transit, sometimes it's just you don't get a transit, it's just a fuzzy thing. And then sometimes you very rarely you have stars that are pulsating in brightness. I nickname these strobe lights because they're rapidly brightening and diminishing in brightness. So with these stars, it's very hard to find a transit. All right, next slide.
So moving on to exoplanets, an exoplanet that I did was WASP-41, and usually WASP planets are known for how large the radius is, and so if you look here, we have our archive observations, and on this light curve graph, you can notice that there's 7 different transits. So moving along, we found the folded light curve with the transit depth. So we zoomed in, and so after doing that, we found our BLS periodogram. And so for my research, I found out that the period was around 3 days, 3.0535 days. And so on the archive period, which is what we got from the NASA Exoplanet Archive, it got to a 3.0524, which you could see there's a lot of, it's pretty much off by 0.001. So there's not much of a difference. So we know that so we know that the archive and my research checked out. And so after placing our, continue on to our light curve, I placed it into a scatter plot, and I found out that the depth was 2.1%, and the radius of the planet was around 1.168 radius Jupiters. So this planet is a bit larger than Jupiter's radius if you were to compare them. Next slide, please.
So the planet I did was WASP 18b. Now, like Wilson said, WASP planets are known for being very big, and you can see that from the scatter plot that I made. It's a very deep drop. The depth, however, is 1.03, and the radius of the planet is 1.24 RJ, which means it's 1.24 times the size of Jupiter. The period of the transit that I measured was 0.924 days from 0 to the biggest increase of light, biggest transit. All right. Next slide.
So in conclusion, and a few next steps that we're planning to do was this week, we found some interesting planets on the Exoplanet Archive. We downloaded our data and we used these planets from the Space Telescope. We also measured the period and radius of these planets and compared our results to a bunch of archive values made by other scientists. So in the future, what we're planning to use with this method was that we could try to measure the radius of other smaller planets, since most of our research was from these really large planets. And we could even try finding some new planets that might even be habitable from the conditions. So thank you for listening, and we want to say huge thanks to the Institute for Astronomy, the University of Hawaii, the NASA Exoplanet Science Institute, HiStar, J.D. Armstrong, Carolyn Kaichi, our mentors, Nick Saunders, and Jordan Bond.
All right. Well, thank you guys very much. Are there any questions? Again, we will try to get them to you as soon as we get them, and hopefully in a timely manner. There is a little bit of a delay on the video, so. Oh, yes. Okay. So we have a really, this is a really good question that I think you guys are going to have a great answer for. You said that you planned on finding the temperatures of exoplanets.
Yeah.
How would you have done that?
So we haven't really gotten into depth with how the process, but from our programming, we're using this program called Lightcurve, which we explained earlier, and it's basically a software based off of Python. And from this, we could actually find the temperature of the exoplanets in a more effective and efficient way.
Okay. The next question I have is, what is the spiky stuff in the transit of WASP 77AB? And so let me go ahead and share that. So that.
Okay, so what the spiky stuff was, if you're asking about the zoomed in transit, if you look at the image above it, it's not like completely flat. It waves up and down a little, and that's just due to like the star brightness going up and down a little. You can flatten it in the light curve coding, but sometimes when you do flatten it, it makes it worse, which it did for me. So I just chose to left it. So basically, what this spiky stuff is just it's just like a disturbance, or because they're not all equally level, but you can still see the actual transit. So.
Okay, so basically, let me confirm that I understood your answer. The spiky stuff is caused by this variation in the star, and when you line those up, it ends up being kind of spiky like that.
Yeah, because sometimes the star is brighter and it's dimmer, so then the actual brightness drop is different, so it varies a little bit.
Excellent. We have one more question, unless somebody else comes in. Actually, two more. So across all the systems you analyzed, were your measured planet sizes consistent with those with the from the Exoplanet archive?
Yes, from a majority of our planets that we were looking through, a lot of them had the same or very close to the other exoplanets archived on the NASA exoplanet archive. And so we could, at most, there was slight differences, but that could be due to our precision aiming from like having the X line being placed, which you could see on the scatter plot, which is that blue line. And it basically differs from the dip of our light, from the brightness of the light.
Okay. And this is kind of an interesting question that is sort of applicable to any project, I think. Can there be an unknown variable which may change your results?
From looking at it from the standpoint, I'm not exactly quite sure if there's any, but fast forwarding, maybe there. I doubt that there could be anything from our research, but if there is, our results deferred a different answer.
All right. Okay, and then we've got one comment that just showed up from Jennifer, and it is woot woot. So in other words, I think that there is some applause there. Okay, I think we're going to go on to the next question, or to the next group. Lauren Weiss did ask a question, and I think that the answer would be yes. So, oh, and there's one more. Jordan says, I'm so proud of you guys. So good job. All right, our next group, let me switch to the right page here. Excuse me, we are experiencing technical difficulties. Please stand by. Okay, so our next group is determining the age of star cluster Ruprecht 121. The team members of this are Annika and Chetta. Annika is a returning high star student. She's done work on supermassive black holes, measuring the mass of a supermassive black hole. And Kevin Martin, who is a new student to the High Star program, they've been working with Ryan Dungee. Ryan's a graduate student over at the University of Hawaii Institute for Astronomy, and Celeste Young and Allen. Celeste is a college student, and she's one of the alumni that we've convinced to come back and help these students do that with their projects. And so if you guys are ready, now did you send your slides to me, or are you guys?
I'm gonna present it.
Okay,
Yeah.
great, good. Okay, I'll turn the time over to you.
Okay, so hi everyone, I'm Kevin.
And I'm Monica.
And our project is on determining the age of the open cluster Ruprecht 121.
Okay, so first of all, what are star clusters? So star clusters are groups of stars bound together by gravity. They can be separated into two types. First, there's globular clusters, which are usually very old and bound together very tightly, and open clusters, which are usually younger and loosely bound. And for this project, we focused on the second type, open clusters. So why does this all matter? Well, open cluster stars are all born at the same time. This means that they're all roughly the same age, and the only difference in these stars is their mass. So open clusters help to refine our analysis of observations of stars to determine their properties.
So I'm gonna go over some basic terminology that we use. So photometry is measuring the intensity of light. So if we have an image from a telescope like this, photometry is basically looking at these points of light coming from the stars and then measuring how bright they are. APT is the software that we use to conduct this photometry. And bands are filters on a telescope. So if you look at this image, we can see this picture of a hibiscus. And you can also see that it's split into 3 bands. So we can see red, green, and blue. And when you combine the 3 bands or filters together, you can get a full color image. And I was trying to think of a way to explain isochrone. So I came up with this graph. And if you see here, you can see these lines. And these are the isochrones. These lines are the isochrones. You can see in this middle line, there are higher people who have a lower weight and also shorter people with a higher weight. But all the people that fall on these lines are about the same age. And if you look here, you can see shorter and smaller are babies. And then we've got tall and heavy people, which are adults. And so the isochrone is a computer generated model, and different isochrones represent different stages of a life cycle. So you can see this one represents being a baby, this one's, school age, and then here's being an adult. And even though the points on the line have different physical properties, everything that falls along the line is the same age. So the first thing we did is we had to generate a source list. So if you see this image from the telescope, generating a source list is basically finding all the points in the image where the stars are so that we know what to analyze. Then we process the image, which is basically associating a number to each point. And then we can export that as a text file. So you can have a big list of all the data points, and then that makes it easy for our programming to read the data.
After we export the text file, then we import it into Google Colab. And from there, we use Python coding, so it's easier for the computer to read it and plot the data onto a graph. So the first thing that you do is convert the data to a usable standard, and then you get the absolute magnitude by subtracting the distance modulus. Okay, so 2 stars, they might have the same brightness or overall brightness, right? But when one is closer to you, then it'll appear brighter, and one that is farther away from you will appear dimmer. So by subtracting the distance modulus, we can get the actual brightness of the stars. After that, you find the difference of two band intensities to get color. So one way that I found really helps to explain it is that one star might appear really bright in blue, but that doesn't necessarily mean that the star is blue. It could also be brighter in green. So by finding the difference of two bands, then you can get the actual color. And then after that, you plot the color against one of the bands to find the overall brightness of the image.
So when we analyze the data, the first thing we have to do is determine which of these points are actually useful. And if you look at this, we've got a really wide spread and there's a lot of noise here. And a lot of this comes from, there are stars in the background and the foreground that can interfere with our measurements. So you get a lot of points just all over the place. So we mainly want to be focusing on a lot of these points that follow along the main sequence. So that's around here and some up here. And then we want to find the turnoff point. So Dr. Van Saters actually shared this video with us first a few days ago. And I thought it was a really good visual representation of what the turnoff point is. So if you see here, this is passing through time. And these really high mass, bright, hot suns, they're starting to peel off from this main sequence right here. And as they get older, that's how you can tell how old this cluster is. But by looking down here at the bottom, you're not really getting any data because throughout time, those stars don't change very much. So we want to be focusing on where those higher mass stars are peeling off from the main sequence. So if we're looking at the data over here, you can see there's nothing really up here. And then you can see a few stars starting to peel off from that main sequence. So if we plot a bunch of these isochrones on the data, we can find one that matches all of our points. And then that is how we can determine the overall age of the star cluster.
Okay, so as you can see here, these are our data points, and we plotted a bunch of isochrones over that. On the x-axis is the B minus V, or blue minus green magnitudes. So this basically gives us your mass. And on the y-axis is the V magnitudes, which is one band, and this gives us the brightness. So as you can see, from where the data points are, we tried to plot where it peeled off the most, and we got an isochrone that detailed that the age of Ruprecht 121 is around 150 million years.
Okay, so thank you to Ryan Dungy and Celeste Jonga-Nealon for being our mentors through this process. Also, thank you to JD Armstrong and Carolyn Kaichi for making this whole program possible. And also thank you to all the people who, all of these awesome people who came to share their knowledge with us in the field and give exposure and yeah, just share their time with us and their knowledge. And thank you to all of you for listening to our presentation. Are there any questions?
All right, well, I will feed the questions to you as they come in, and so far we've been able to do that in a timely manner. There are two comments that have come in, and that has spawned a question from me. The first comment is heart isochrone plot, and the second comment is from Dr. Huber, which is best isochrone explanation I've seen. And my question is, do you mind if I keep that? Because I love it as well.
Yes, you can keep it.
All right. Okay, so if there are any questions, please feel free to send them to us. You're getting a lot of applause on the chat room. give it a moment longer for some questions to come in. And if not, we'll move on to the next group with, yeah, you guys are getting a lot of applause, seriously. All right, and including from somebody you may have heard of, Nick Saunders, another one, Celeste Jongenelen. So great, I think you guys have done a great job. Oh, Jamie Taylor, I hope that I'm pronouncing your name right. The question is this the age that you expected? So maybe is it the age that was published?
Well, compared to data that other more qualified scientists, I guess, got, overall, we were a little bit young compared to what they got, but yeah, it was pretty close. So that was good. That was kind of nice to hear, you know, that we did something decent, I guess.
All right, so you guys came in a little young, but pretty close.
Yeah.
We have a question from another person I know over in Manoa, and it has to do with your graph. What are the things that are bluer than the main sequence turnoff point?
Monica?
Bluer as in?
I think he means like these points here.
Oh, the points over there. Mostly all of it was just noise because when we I don't know how to explain it. Okay, so when we subtracted the distance modulus, there were stars in the background and the foreground that were part of the image. We didn't want those in there, and since we subtracted the distance modulus that we took for the stars in the star cluster, they weren't exactly accurate for any of the other stars, meaning that they're plotted the wrong way on the graph. So they're just noise.
Okay, so if I understand your answer correctly, you're saying the data was a bit noisy, and that's probably some of them, and that some of them are probably interloper stars, stars either in the foreground, background, or somehow not associated with your cluster. Is that right?
Yeah.
All right. Okay. We'll give it another moment for any other questions. And I'm not sure how long I need to wait for the delay, but we are doing very nicely on time. Okay. All right. Well, thanks again. Let's everyone give them a nice virtual round of applause here. You've already got it coming in on the chat line on YouTube. And so let's go ahead and move on to our next group. I will be presenting the slides for the next group. So the next group will be talking about the music of the stars. We have Luke Berrigan, Anna Gilbraith, and with the advice of their mentor, Vanshri Balata. I hope I didn't mispronounce your name too severely there, Vanshri. If I did, I am so sorry. Luke is a returning high star student. He's done some work with Oumuamua and looking for the origins of it. Anna is a new student to our program and really great addition, as all the new students have been. And so we will now turn the time over to you guys. And I need to share, I believe. Just a minute, I'm fighting with the computer. There we go. Okay. And technical difficulties hopefully overcome. There we go. We should be sharing. And I'm turning the time over to you. Let me know when you need slides of
Thank you, JD. Hello, my name is Luke Berrigan.
I'm Anna Galbraith.
And our project is Music of the Stars. Next slide, please, JD. So, what is astroseismology? In broad terms, astroseismology is a study of oscillations in the surface of stars. You can see down on the bottom right hand of the screen, it's showing a flat object with oscillations happening in it. Is what happens on the surface of the stars, and that's what astroseismology studies. So, why is studying movement in the surface of flaming balls of gas trillions of light years away important? Next slide.
So astroseismology studies oscillations, aka starquakes, and helps us learn about many different aspects of the star. Some of these include the rotation period of the star and how fast it's moving, and the age of the star. So our project will be focusing on whether the radius of the star correlates with the frequency at the highest power of the oscillation, and if so, how? The convection zone is where these oscillations occur. And just like water, it causes movement. The bottom right shows kind of how it looks. Next slide.
So, the method is what we did. The first thing we had to do is we had to learn how to code. Basically, the first part of our code was to actually download the observations from the Kepler Space Telescope, which you can see in the bottom left-hand corner. On the right is just a little kind of snippet of the code that was used. It was a little bit longer than that, but we couldn't really fit it all in one page. Once we had the images downloaded, we ran it through the next part of the code, which is on the next slide.
So the light curve for the star Papa U. Papa U was the first star that we did all of this on, and we were kind of lucky because the oscillation was pretty observable. But the graph below shows the light curve that we made first, and it goes over the course of 30 days. It'll show the flux of the star over the course of 30 days, also known as a quarter. Next slide. So this one is pretty much the first one again, but it gets rid of all of the unnecessary data that we don't need. And pretty much, yeah. So next slide.
So the power spectrum, this is basically the first two graphs, but replotted as power on the y-axis and frequency on the x-axis. This basically takes all the powers emitted by the star and plots them over frequency. You can see circled in the pink circle is the oscillation that we're actually looking for. So next slide, JD, please. On this slide, it shows basically we just got rid of all the unnecessary data now that we knew where the oscillation actually was. And we took a line and we plotted it where the highest power was, and we found out which frequency, which was about 2,200 something. So yeah, you could see it was pretty obvious where it was and what the oscillation was doing. So next slide, JD, please.
So these are the light curves from a star that I did, the numbers at the top. And one on the left is just like the original light curve from the previous star we were just showing. And the second one is after we got rid of all of the unnecessary data. Next slide. So the thing is, we couldn't observe where the oscillation is. So instead of finding the statistical value, we found the theoretical value of where the oscillation should be. We added this code on the right to help us find it. And using the radius and the mass of the star, we added this code to find the new max and the estimation of where the oscillation should be. Next slide. This is the final power spectrum. And as you can see, the statistical value should be near the 150, but instead it's a little bit more towards the right because this is the theoretical new max. Next slide. Next slide.
So this next few set of images is just another star that I did. As you can see on this first slide, it's just the light curve, which is just a plot of the light output of the star over time. As you can see, there's a lot of very kind of large outliers and yeah. So next slide, JD. Oh. This is also just another one of those graphs with all the outlying data and the bad data removed. Next slide, JD. And again, you can see how there's no really visible oscillation in this graph. So again, we had to find the theoretical new max or the theoretical frequency at the highest power. Next slide. And this is where it is on the red line. It's just kind of somewhere there, even though there's things higher than it. Next slide. So limitations. On the last two stars, we couldn't really see where the oscillations were. And a few things that could have caused this is light from the sun's reflection off the earth. So we're getting interference from the sunlight bouncing off the earth. Unwanted instrumental noise, like on the electromagnetic spectrum from different instruments, including the telescope itself. And noise from the star because of stellar granulation, which you can see in this image. It's kind of like, yeah, like it says in the slide, it's similar to bubbles, and it makes it so that you might not be able to see the oscillations. Next slide.
So I just wanted to add this in because some of you might not know what a light curve or a power spectrum is. So a light curve, pretty much it plots the light over the time of the star. And a power spectrum looks at all the frequency the star generates and plots their power at different frequencies. So yeah, just to stop any confusion that might happen. But conclusion, how does the frequency at the highest power relate to the radius? Once we had all of the new max values for the stars, we plotted those values against their star's radius. This was what we originally intended to do. On the right is a chart that kind of has like a downward curve to it. And so if you notice, as the radius increases, the frequency at the highest power decreases. So if you kind of relate it to an instrument, the larger the instrument, the deeper the sound, or the lower the frequency. It's the same with stars. Next slide. So,
thank you.
Any questions?
All right, well, thank you guys. And my apologies, I got a little off on the slides there a couple times. So you guys so our internet audience, you should know not to blame them, but to blame me. Let's see here. And so we're waiting for questions, and you're getting some nice applause again. So you said that you thought that one of the possible sources of error could be the solar granulation or the stellar granulation. Is that right?
Yes.
So how would that kind of work?
You want to take this one?
So the oscillations that we're looking for are from the inside of the star, and it's more like earthquakes. And the granulation that would be interfering with those is kind of more like if the ground of the Earth started bubbling. It's causing movement in the star, but it's not the movement that we're looking for.
All right. Getting more applause on here. So you guys have obviously done a great job. We'll give just another moment for other questions, any questions to come in. Okay, I'm not seeing any questions. Let's see here. Oh, we just got a question. Here we are. Why do you think the light from the sun redirected off the Earth is getting in the telescope?
I think it's because, well, the telescope is obviously not trying to look at the sun if it's looking at other stars, because that would just cause a lot of unnecessary light that would be interfering. But if it's bouncing off the Earth, sometimes it's unavoidable that a little bit of the light gets reflected into the telescope. So, yeah.
All right. And we've got another question here. This is actually one that I was kind of wondering myself. What is the motivation for the title of your talk, The Music of the Stars?
Anna, do you want to answer this one?
Yeah, sure. So one of the questions on a worksheet that we got before we even did this project, it asked if there was any relation between sound and pressure. And so we kind of just answered it the best we could. We just said that vibrations kind of had to do with both of them. But the star, it creates vibrations that we're actually looking at. And since vibrations are kind of related to sound, we're like, it's kind of like music. So, yeah.
Yeah. Also, if you actually take these frequencies, you can listen to them. And so if you search up, we should have put the link to this website in the slide, but we forgot. You can find actually audio clips of these frequencies, and it's kind of like music. It's interesting to listen to. So that's kind of also the reason.
All right. Well, I think that's all the questions that we have for you. Thank you very much. I know that a lot of people online are giving you a standing ovation, as many of this, as everyone seems to be getting. Great job. And we're going to move on to our next group. We have Quentin Wong, who is a new high star student. You heard from his brother earlier today. And also Thomas Harding, AKA Tag. I hope that you guys, you wanted me to introduce you as Tag. Tag is also a new student. He started an astronomy club over at Kihei Charter School. So if anyone is over at Kihei Charter and is interested in astronomy, this is probably the guy to get hold of. And they've been working with Anna Payne, who's a graduate student over at UH Manoa. And Anna has helped a number of students working at the High Star program, including Annika. And the Quinton and Thomas's project is determining the solar mass of a supermassive black hole. So they're going to be telling you how you measure these supermassive black holes at the center of galaxies. And I will start sharing the presentation here and turn the time over to Quinton and Anna. Is it Quinton and Anna? Quinton and Thomas, sorry, Quinton and Tag, apologies.
I'm taking it as a no. All right, my
There
mic.
you go, we can hear you now.
All right, thanks for having us. I'm Tag, as you may have heard, as we were introduced, and this is our project we've been working on all week. Next
And
slide.
I'm Quinton Wong.
Next slide. Galaxies are groups of gravitationally bound stars, gas, and dust. At the center of a galaxy is a supermassive black hole. And when that black hole, give me a sec. The center of a galaxy is a supermassive black hole. And when that black hole is actively accreting material, it is called an active galactic nucleus. As we do have a slide. An active galactic nucleus is located at the center of a galaxy. It consists of a supermassive black hole, a accretion disk, and the broadline region in the dusty torus. We'll get to we created a slide for that, and we'll get to that soon. Supermassive black holes cannot be imaged directly, as we have learned from last year. So we have to use indirect means to study it. A technique to measure the black hole's mass is called reverberation mapping. We're going to get to that soon. We measured the H-beta emission line fluxes over time to obtain light curves, and then measured the time lag between the H-beta light curve and the optical D-band photometric light curve to estimate the black hole mass. Next slide, please. This is an active galactic nucleus, as I was speaking about. They are located at the center of a galaxy. Well, black holes are located at the center of each galaxy, but these are special black holes. The accretion disks is a material pulled near and into the black hole. Radiation is emitted from the accretion disk and the jets, as you can see right here. As this radiation approaches the gas in the broad line region, energy re-radiates. Determining the time it takes to take each broad line region to an accretion disk, known as time lag, helps estimate distance and therefore solar mass. As you can see from the lovely image we've provided, this is showing an active black hole and what goes on with it. Next slide. One of the techniques that we've used, known as reverberation mapping, was used to estimate the mass of the black hole at the center. This is how we did it. MBH equals, that's it. So thank you. That's the formula. That's the formula for it. As you can see, with this, and we've taken if you're wondering about the images we found, we were taking it from, I think, Chandra, from the Chandra website, and we've been using these. I'll take it over to Quinton for the next slide.
Okay. So as Tag previously talked about in the active galactic nucleus slide, and a pretty important part of our project is using time lag. And so to get a bit more into detail in that, first of all, if we look at the picture that's on the left side of the slide, first of all, these are examples of light curves showing the H-beta emission line, which is the part that we're focused on, and then the continuum. These are both from the same galaxy. And you may notice that both the lines are pretty similar in shape, but it looks like the red one at the top is shifted over a little bit more to the right compared to the blue one. And so the difference between those, highlighted by the pink line, is called the time lag. And so we use a program called Python. And what Python does is it compares these two light curves using a process called interpolation. And so to put interpolation really simply, it basically just means that the program looks for 2 points, and then it estimates where it thinks another point might be in between those 2 points. And so the time lag, again, is used to measure the distance between the accretion disk and the broadline region. So it kind of finds the distance, how long it takes for the radiation to echo. And then we can use that later to determine solar mass. So JD, can you go to the next slide, please? And so spectra. So when we first get our data, we get them as a bunch of different data files. So first we have to compile them into a spectrograph. So this graph is used to compare the wavelength against the flux of a distant object. In our case, the distant object is the supermassive black hole, because we have to remember that black holes are actually super, super far away. And even though they're really, really big, because they're so far away, we can't observe them directly. So we use these spectra data and to create the spectrograph. And so our focus, our area of interest, is the H beta line, which, as you can see in the graph, is highlighted by the red arrow, that kind of wide base part. And that usually has a wavelength of around 4,862 angstroms. And so again, we use Python, which is essentially like a computer programming, to create these plots from the spectra data, which is collected from the Sloan Digital Sky Survey. And for those of you who are not familiar with the Sloan Digital Sky Survey, basically it's a survey that collects spectra data from millions of objects, like the spectra data we've used today. So this is the spectrograph that I created from my object LC272. Okay, next slide, please. Okay, so Gaussian curve. So after we've created our spectra graph, we now want to focus on the H beta line, which is the part that we're using. And so we create what's called a Gaussian curve. And to put it simply, a Gaussian curve is just a mathematical model. In this case, it's showing the distribution. For us, we're using it to show the distribution of flux, but you could think about it like a bell curve. It's a common shape that comes up in like statistics a lot. So we create this Gaussian curve to best fit the H beta line, which is again the part that we're focusing on. And so we set multiple parameters to help best fit this H beta line with the Gaussian curve. So that includes the amplitude of the curve, which is how high or how tall that curve is, the width, how wide it is, and then the center. So that's where the center of the curve lies approximately. They're all estimates, but we just try to do it as well as we can so that we get an accurate Gaussian curve. And then one thing you may notice from the previous slide is that we have isolated just this part. And part of the way we do that is we set continuums. So if you can see on the left part, we kind of set continuums or like kind of like a baseline. So what that helps us do is it sets the next slide, the slide after this, at like the baseline of 0. And so Python, again, we use Python quite a lot for this, then integrates, which basically just means it finds the area under the curve, under that Gaussian curve, and then it gives us the integrated flux. So next slide. And so from here, we create what's called light curves, which I'm assuming, based on how many people have already done it, hopefully you're familiar with what a light curve is. But and just as a quick refresh, it just compares the brightness of an object, the flux, over a period of time. So we use these graphs to compare the galaxies. So these two pictures are the light curves for the galaxy that I was using. So on the left-hand side, we have the H beta light curve. So that's the graph that I made. And the bottom right-hand corner, we have the continuum light curve. That one I did not make, but we do use it for our comparison. And regarding the units of the light curve, the bottom is the time, and that's MJD, or median Julian date. The MJD comes about basically a date, like some arbitrary date in the past was called day 0, and then every day since then has been like day 1, day 2, day 3, etc., up until In this case, we're like at 56,000 around there. And then we also, you may notice, we use the integrated fluxes from the previous slide that we just talked about. We integrated the Gaussian curve. And so we run this through Python and comparing the H beta curve to the continuum light curve, and then it finds the time lag that we were talking about earlier, which is how much the H beta curve has been shifted. And for this one, for mine, it was 4 days. And again, we're using Python, which is a pretty integral part of this. We calculate the time lag, which is 4 days, and then we run that through Python, and we get the solar mass for my galaxy LC272 is approximately 1 times 10 to the 7th 1 times 10 to the 7th solar masses. And a solar mass is just another unit of measurement. It's approximately equal to 2 times 10 to the 30th kilograms. And part of the reason we use solar masses in the first place is because in astronomy, values are so large, it'd be a little bit difficult and maybe a little bit annoying to have to use such large numbers. So by setting a solar mass at such a large quantity as a standard, it makes it a lot easier when trying to describe even larger quantities than the mass of the sun. And I guess in the grand scheme of things, like when we talk about the importance of studying galaxies, why do we study them in the first place? Studying the central areas of galaxies can allow us to better understand the environment around the black hole itself. And from there, we can learn more information about the galaxies themselves. It's quite remarkable how something so massive and so distant can be measured just through peaks and values of a light curve.
Yeah.
And then lastly, we'd just like to acknowledge our mentor, Anna Payne, JD Armstrong, Carolyn Keiichi, all the amazing speakers that we've had throughout the week, and the Institute of Astronomy for providing us with such an amazing educational and fun opportunity.
All right, well, thank you. Go ahead and stop sharing here. And we already have a question for you. If you're ready, we'll first give you a virtual round of applause, of course, and you're receiving that a little bit online. You have a question already. So you said that you integrated under the Gaussian curve, and the question is, why not just integrate under the line itself? The line looks skinnier in the center than a Gaussian.
Okay, so part of it is, from my understanding, you can't really integrate, or I don't think the program had the capability to integrate the spectra data just like as it is. And so the reason why we use a Gaussian curve is we get an estimate. And part of that, I think I might have forgot to mention it, is we actually do use there are like error bars too. So in other words, if you go back to the light curve, I don't know if you can go back to the light curve slide, JD.
Back to the light curve slide here. And I'll probably want to share it so that people can see it. Wouldn't that be clever? Okay, there we go. We're back to the light curve analysis slide.
So if we go back to the light curve analysis, we can see that, so those long vertical lines, those are called the error bars, which basically tell us, because in science it's important to note, how accurate our measurements are. And so in my case, as you can see, the error bars are quite long, and like for the sake of for the sake of our first project, we kind of just went with it. But I think in order to get like a more accurate reading, you would try to like minimize the length of those error bars, try to get as close as you can. But I guess the reason why we can't just integrate that spectra is because my understanding is that it's not capable of doing that. So instead we have to use like a best estimate to do that. But for sure, we could have definitely tried to get like a more accurate reading of the integrated flux. But considering this was the first time doing it, I think we did a pretty reasonably accurate job of doing that.
All right, yeah, I would agree that for the first time doing it, you're doing great work. If I understand your explanation, probably if I were to put it in a nutshell, you might say, well, this is the first time doing it. And this tends to be a pretty good way to fit a Gaussian and just calculate the known integral of a Gaussian. Is that a fair way of saying that?
Yeah, I would say so, yeah.
Okay, wonderful. We'll see if we've got any other comments online. We've got quite a bit of applause for you guys, so you can go ahead and take a bow. You both did excellent. And we'll see if anyone else has a question. If so, please let us know. And I'm going to stop sharing here so that I can check in the chat window, see if anyone locally has any questions. All right. Well, the applause just continues for you guys, so bravo. And we'd like to thank you and all of our speakers. This concludes this year's presentation of the High Star students and the work that they've been doing. And thank you all. I think you did an excellent job, and we'll be sending you your diplomas in the mail because we're doing virtual this year. All right.
Thank you.
All right, and thank you.
Thank you.
Let's give yourselves give everyone a big hand. Give yourselves a big hand because you've really earned it.
Oh boy.
So we're turning on the cameras so that everyone can see you as they give you the round of applause. So if you have not turned your camera on, please do. Couple more if you need to turn your cameras on or not.
Good job, Professor Wong. Good job.
All right. And so the students, I want you to hang around for a few more minutes.